Surface chemistry, adsorption phenomena, isotherms, and catalytic applications. Surface chemistry examines physicochemical processes occurring at interfaces between phases, such as solid-gas and solid-liquid boundaries. These interfaces exhibit structural and energetic heterogeneity, making them fundamentally distinct from bulk phases. The complexity of surfaces, aptly captured by Wolfgang Pauli's remark that God made solids, but surfaces were the work of the devil, arises from structural heterogeneity, electronic anisotropy, and dynamic interactions with surrounding phases. The field developed from early empirical observations, such as the use of charcoal for decolorization in the 18th century, to a quantitative science grounded in thermodynamics and kinetics. Foundational work by Josiah Willard Gibbs established the concept of surface energy and interfacial equilibria. In the early 20th century, Irving Langmuir introduced molecular-level descriptions of adsorption, which revolutionized catalysis and materials science. Industrial breakthroughs such as the Haber-Bosch process demonstrated the transformative impact of surface-mediated reactions. Fundamental concepts: surfaces, adsorption, and absorption. Atoms at surfaces experience incomplete coordination, resulting in excess surface energy and enhanced chemical reactivity. This drives processes such as adsorption, catalysis, wetting, and corrosion. Real surfaces are not ideal. They contain terraces, steps, kinks, and defects, each offering distinct adsorption energetics and reactivity. Adsorption refers to the accumulation of atoms or molecules at a surface, forming a two-dimensional phase distinct from the bulk. In contrast, absorption involves the penetration of species into the bulk material, as observed in hydrogen uptake by palladium. The distinction is critical in catalysis and materials design, where surface versus bulk interactions determine performance. Physicochemical and chemisorption. Adsorption processes are broadly categorized into physicochemical and chemisorption, which differ in interaction strength, reversibility, and thermodynamic behavior. Physicochemical arises from weak van der Waals forces and is typically characterized by low enthalpy changes, reversibility, and the possibility of multilayer formation. It is strongly influenced by temperature and pressure, resembling gas condensation on surfaces. Chemisorption, by contrast, involves the formation of chemical bonds between adsorbate and surface atoms. It is highly specific, often irreversible, and typically limited to monolayer coverage. Chemisorption may occur via molecular adsorption, in which the molecule remains intact, or dissociative adsorption, in which bonds are broken upon interaction with the surface, for example, H2 dissociation on metals. In many practical systems, both physicochemical and chemisorption coexist, leading to complex adsorption behavior. Adsorption isotherms. Langmuir theory. Adsorption. Isotherms describe how the amount of adsorbate on a surface varies with pressure, or concentration, at constant temperature. Among these, the Langmuir isotherm remains one of the most influential models in surface chemistry. Theta equals Kp divided by 1 plus Kp. The Langmuir isotherm models the fractional surface coverage, theta, as a function of gas pressure, P, where K is the equilibrium adsorption constant. It is derived by equating the rates of adsorption and desorption under dynamic equilibrium conditions. The theoretical foundation of the Langmuir model rests on several key assumptions. Adsorption occurs on a finite number of identical sites. Each site can hold only one molecule, monolayer coverage. There are no interactions between adsorbed species, and adsorption is reversible. Despite these simplifications, The model provides remarkable insight into adsorption behavior. At low pressures, the isotherm reduces to a linear relationship between coverage and pressure, indicating that adsorption is proportional to the number of available sites. At high pressures, the surface approaches saturation, and the coverage approaches unity asymptotically, reflecting monolayer completion. This saturation behavior distinguishes Langmuir adsorption from multilayer models. One of the most significant applications of the Langmuir isotherm is in determining adsorption equilibrium constants and thermodynamic parameters such as adsorption enthalpy. By analyzing temperature-dependent adsorption data, one can extract the heat of adsorption, providing insight into the strength and nature of surface interactions. The Langmuir model is also extensively used in catalysis. Surface coverage predictions enable the development of kinetic models for heterogeneous reactions, particularly in the Langmuir-Hinshelwood mechanism, where reaction rates depend on the coverage of reactants on the catalyst surface. In such cases, the rate expression incorporates Langmuir-type adsorption terms, linking macroscopic reaction rates to microscopic surface processes. In materials characterization, the Langmuir framework aids in estimating surface area and active site density, especially when adsorption is limited to monolayer formation. It also finds applications in environmental science, such as modeling pollutant adsorption on activated carbon, and in biotechnology for protein surface interactions, although deviations often occur due to surface heterogeneity. Despite its utility, the Langmuir isotherm has limitations. It does not account for surface heterogeneity, lateral interactions between adsorbates, or multilayer adsorption. These limitations led to the development of alternative models such as the Freundlich and BET isotherms, which better describe real systems under certain conditions. Freundlich isotherm is an empirical model describing heterogeneous surfaces, applicable to multilayer adsorption and non-uniform energy distributions, whereas BET, Brunauer, Emmett, Teller, extends Langmuir theory to multilayer adsorption, widely used for surface area determination using nitrogen adsorption. Surface chemistry in catalysis. Surface chemistry is central to heterogeneous catalysis, where reactions occur at the interface between phases. The catalytic process involves adsorption of reactants, surface reaction through intermediate species, and desorption of products. The catalyst itself remains unchanged in composition, although its surface structure may evolve during operation. The effectiveness of a catalyst depends on a balance between adsorption strength and reactivity. According to the Sabatier principle, optimal catalytic activity is achieved when adsorption is neither too weak nor too strong. Weak adsorption fails to activate reactants, while strong adsorption can lead to catalyst poisoning by blocking active sites. Industrial catalysis relies heavily on surface processes. In the Haber-Bosch process, nitrogen and hydrogen are activated on iron surfaces to produce ammonia. Similarly, catalytic converters use platinum group metals to transform toxic exhaust gases into less harmful products. Hydrogenation reactions, such as the conversion of vegetable oils into solid fats, occur on nickel surfaces via adsorbed hydrogen atoms. At the molecular level, catalytic reactions often involve bond dissociation upon adsorption, followed by recombination into products. Surface structure, including defects and crystal orientation, plays a critical role in determining catalytic activity and selectivity. Modern catalysis increasingly focuses on tailoring these surface features to optimize performance. Applications and modern developments. Surface chemistry underpins a wide range of technologies. Adsorption processes are used in gas purification, environmental remediation, and chromatographic separation. Activated carbon and zeolites selectively adsorb gases based on molecular size and polarity. In medicine, adsorption plays a role in drug delivery and antimicrobial action. Recent advances have expanded the scope of surface chemistry into nanotechnology and energy applications. Single-atom catalysts maximize atom efficiency and provide well-defined active sites. Metal-organic frameworks, MOFs, enable highly selective adsorption and storage of gases, such as CO2 and hydrogen. Two-dimensional materials, including graphene, offer unique surface properties for sensing and catalysis. Electrocatalysis and photocatalysis represent frontier areas, where surface processes drive energy conversion reactions such as water splitting and carbon dioxide reduction. These developments are central to sustainable energy technologies. Surface Characterization, SEM and XPS. Understanding surface structure and composition requires advanced characterization techniques. A scanning electron microscope provides high-resolution images of surface morphology, revealing features such as roughness, porosity, and particle size distribution. It is widely used in materials science and catalysis research. X-ray photoelectron spectroscopy offers elemental and chemical state information with nanometer-scale surface sensitivity. By measuring binding energies of core electrons, XPS can identify oxidation states, chemical bonding, and adsorbed species. This makes it indispensable for studying catalytic surfaces and reaction intermediates. In conclusion, surface chemistry provides a molecular framework for understanding interfacial phenomena that govern adsorption, catalysis, and material performance. From the foundational work of Irving Langmuir to modern developments in nanostructured catalysts and operando spectroscopy, the field has evolved into a cornerstone of contemporary science and technology. Its continued advancement is critical for addressing challenges in energy, environment, and advanced materials.